Okay, this is going to be a fairly long clip, and this is probably the most complex piece then of this unit. Okay, so what we need to remember is that neurons have two properties that we allow us to conduct impulses. One of them is the ability to be irritable or to sense change. That's the receptor part. And then the other one is conductivity, taking that information and taking it and moving it somewhere. Okay, and that's the conductivity part. So I think what I need to do is go to a picture here because this is a little bit complex, and I'll talk through the picture. Okay. So I'm going to slip through several slides here, okay? And I'll talk my way through the slide. Okay, so when a neuron, a membrane is at rest, it's said to be inactive. I like to think of it as sleeping, okay? And that means the inside is negative with respect to the outside, which is more positive. Now don't, just listen to it through and then we'll summarize it. So polarized or sleeping, if you will, means that there are fewer positive ions inside than the outside surrounding tissue. In other words, that we're looking at the inside being overall negative and the outside being overall positive. Remember that the major intracellular ion is potassium and the major extracellular ion is sodium. And what you see in this first picture is sodium outside and potassium inside, and that's the normal way for it to be. So if the inside is negative and the outside is positive, then we don't have anything going on, okay? And so we need some kind of stimuli. So along comes a stimulus, light, sound, pressure, a neurotransmitter, something like that. And that causes a change in the polarity. It excites the membrane. So what we have then, the cell having some change briefly. So sodium ions cannot slip into the cell here because they can't get in. It's a high to low thing. Okay, there's actually gates there. So eventually what happens is that the sodium gates open up. And sodium then diffuses. So the stimulus comes along, the little gates open up, and that allows sodium to go in, high concentration to low concentration. So now what we have is a change in the polarity, and we have depolarization. So now we've got more positive inside than outside, okay? And that's depolarization. This is polarized or sleeping. That's a Z, all right? Now, the threshold potential is the amount of stimulus needed to cause the membrane to change its polarity. An action potential is a nerve impulse. An action potential is a nerve impulse. Okay, same thing. If we have an action potential coming, okay, it's an all or none response like we talked about in the muscle. It's either going to happen or it isn't going to happen. It's not partially going to happen. The impulse never goes partway along a healthy neuron. So once the sodium ions have opened up, they slip inside the cell, then those gates shut, and we get an opportunity for potassium to slip out, and that's what you see here. Okay, so we get potassium channels to open. Now what we have is we've restored the polarity, positive versus negative. So we're happy again. The only problem, and that's repolarization. The only problem with that is that now we have the players on the wrong side of the fence. So sodium's inside and shouldn't be, and potassium's outside and should be inside. So we need to restore that somehow. And what we'll do is we will then cause we will start shifting it back in. And I'm just going to take you back to a different little picture here. Okay. So first of all, this is the cell membrane, and remember when we talked about a cell membrane, it's a double layer of phospholipids, and there's often channels throughout it, okay? And those are the gates that would open up and allow potassium and sodium to move. So we have the situation where we have sodium inside and potassium outside. So we've got to now get them back to where they should be. So we call in what we call the sodium potassium pump. And remember, this is a kind of active transport. So this rapid acceleration, so what we have, let's review it again. We have a sleeping resting membrane. The stimulus comes along and these channels open up and sodium rushes in. That stops, and then the channels open up the other way and let potassium go out. So this is depolarization and this is repolarization. Whoops, sorry. In order for it to be polarized again, we have to get everything back to the right side. So we call in the sodium potassium pump. So that's it happening. So what we have is this happening in the first section. So we have polarized, depolarized, repolarized. Then we go to the next section. Polarized, depolarized, repolarized, and it goes all the way along the length of the neuron, this activity. Now we have simplified it by that, but imagine one of the gymnasts with one of those ribbons, and they flick the ribbon at their wrist, and the ribbon causes a wave all along the ribbon. And that wave is just like what's happening in your neuron. Polarized, depolarized, repolarized. Polarized, so, and then we have the sodium pump. Polarized, depolarized, repolarized, all the way down. And this is what we call the propagation of a nerve impulse on an unmyelinated fiber. Myelination, though, happens at a faster rate because if you remember, a myelinated fiber has those chunks of myelin like this, and instead of it going straight this way, it slimps through this way. Myelin, as we remember, provides an insulation and the impulse can't transfer through. Instead, it swings around it. When this all gets to the end of the neuron, down here, okay, the neurotransmitter gets released. Let me draw a better picture. Okay, the neurotransmitter gets released, and it then connects with whatever it's being transferred. An effector, which is a muscle or a gland, or maybe it's another neuron to stimulate it. Once the impulse has been cleaned up, the neurotransmitter the neurotransmitter needs to be cleaned up by an enzyme in the synaptic cleft. Okay, I think really that this, sorry, backwards, I know, this review piece will really help you. So what we have, the first piece, summarizing it, is the membrane's polarized. That means that the electrolytes are on the right side of the fence and the charge is overall negative. The threshold stimulus is received by the neuron, so light, temperature, sound, that causes the sodium gates to fling open, and sodium wants to rush inside because it's seeking to go to places of lower concentration. That changes the polarity, and we have depolarization. Next then, that stops, those gates shut up, and for brief moments, potassium is allowed to diffuse outward. That in turn restores the electrical charge, but we're left with everybody being on the wrong side of the fence. In other words, potassium's outside and sodium's inside. We call in the sodium potassium pump, and remember this will take ATP. Okay, so if someone doesn't have any energy, they can't make their neurons work, and that happens all the way down the nerve. So we've been through these, okay. So again, there's some definitions to think about here. Continuous, this is an unmyelinated nerve impulse moving in and out on the neuron, on the axon, okay, as opposed to saltatory, where that instead moves along the myelinated nerve impulse, okay. Continuous. It just goes like this, straight down. If we have the myelination, instead of it going straight through, it goes like this, and it moves very quick. The last term in this section, and this is the complicated section, is refractory period. And the refractory period is following a neuron being stimulated. When repolarization has happened, there is a time when the neuron cannot accept the next stimulus until it's all been polarized again, refractory period.